extra weeks where I don't have standard textbook stuff to cover, and I want to talk about the risks from machine learning, AI, and Microsoft Copilot. And then I'll demonstrate a couple of projects, including one which is pretty fun. It's a real vulnerability that came out like 3 days ago in the news, and it is so easy to exploit. The first thing I tried worked, so it's a ridiculously easy project to find a hard-coded key that will unlock Chirp door locks. Anyway, let's start with this AI stuff. So I'm interested in the methods you take to secure AI systems, and we hear a lot of scary things about the threat. People say it's going to have an extinction-level threat from AI. Elon Musk says AI is going to be smarter than humans within a year. Ukraine has rolled out target-seeking Terminator drones that attack Russian targets with no human in the loop. They use machine learning to identify the targets, and they kill them with no human operator in the loop. And I didn't know that had happened already, but it has happened in Ukraine, and things very close to it have happened in Israel. So, the popular press would have you believe we're at the end of humanity and we're going to have killer robots slaughter us all, and it's might as well just give up and die. And I think all that is garbage because AI is not really that powerful. And so to see all machine learning is very simply just fitting a line through some points. That's the most common type, and that's pretty much all it does. So if you want a spam filter, the only point of AI is you're going to make if you want a spam filter, then you're going to teach it. So the reason you use machine learning is because it'll follow your, this is traditional programming. You would examine spam, you would find words to look for, you would write a program that says if it contains this word, if it contains that word, then it's spam, something like that, and then you test it and improve it until it's good enough for launch. This is a normal program that people perform, and that's traditional programming. You study the problem, you write the rules, you evaluate how well it works, improve it until it's good enough, and then you launch it once it is good enough. But this means you have to write a long list of rules, and you have to keep updating them with humans adding the intelligence. In machine learning, you study the problem, you train a machine learning model on examples, it learns all by itself how to tell the examples apart, and you evaluate it and perhaps improve it a few times, and then you launch it. But you don't write the code, you don't know what words it's looking for, there are a bunch of if-then statements. It figures out by itself how to separate them. And so you can automate this. You can continuously keep training it on new examples, and that would adapt to the changing tactics of spammers. So that's a good thing. And so there's a lot of problems to solve with machine learning once you can't use the traditional approach on, or there is no algorithm. Speech recognition, for example, they just train it on a lot of recordings of people rather than trying to find some mathematical measure of what you're saying. They just let AI figure it out. Same thing with brain scans and such. So analyzing images to classify them is done with AI, detecting tumors, classifying news articles to decide what political bent they have, and so on. A chat bot and a personal assistant, of course, like GPT-4. Detecting credit card fraud is certainly a good one to find which transactions are somehow more suspicious than the others. Recommending a product based on your past purchases like Amazon does. They know what you bought and somehow they guess what you're going to buy next. That's a good job for machine learning. All right, so supervised learning is the easiest, where humans have to label all the data. So you label these are good mails, these are spam, and then you train it on that. That's one way to go. So that's classification, like a spam filter, and also regression, where you measure something and then you try to predict new values from it by fitting a curve through this. That's unsupervised learning, though, is when you have a bunch of data but it's not labeled. And what you can do then is you can still separate it into groups. There appears to be a cluster here and a cluster there and a cluster here. So you can separate it into categories. That's one thing you can do. You can also visualize it, make it easier for people to see. And you can hunt and find the most significant components in multivariable things. If you consider a Tesla, it's got a camera with high resolution taking video, and sometimes some cars actually have other things like radar, so it's got a lot of data, and somehow it has to quickly decide whether you're about to hit something and it hits the brakes. So just like your brain does, it has to discard most of the data and find the important data to focus on, and you can do that with AI models. You can do dimensionality reduction to find out what part of the data is most closely correlated with the thing you're trying to accomplish. and throw away the other data to simplify the problem. And then you can do, with unsupervised learning, you can just do anomaly detection. You have some stuff like credit card transactions or products on an assembly line or anything, and they have this variation. You can tell this one is significantly out of the general trend. So you can find the ones that appear to be defective or special, the network traffic that appears to be different than normal network traffic for a online system to detect attacks on the network, and so on. All right, and you can have combinations where you just form it into groups, and then you take examples of the group and send them to a human to evaluate them. So you make supervised data out of unsupervised data. And you can also make supervised data out of unsupervised data by altering images and then training it to fill in the missing part. And this is what you have on phones now. Phones will automatically, you can erase something, it'll fill in the background. They have practiced on tasks like this using automatically created data. So no human had to label it. They just took a real photograph and cut out parts and pieces and have to practice filling it until it learns how to fill in holes in images. All right, then there's reinforcement learning, like where it learns how to play a game or something. It says you go to the fire or go to the water, and you go to the fire, you punish it. It goes to the water, you don't punish it, so it learns to do that. And you can teach them chess or any other activity that a human can do this way. So that's what AIs are. And they're not all that scary at all. They're very, very stupid. And the large language models talk like humans, but they don't understand the meaning of the words or what they're talking about at all. So to secure these systems, a lot of people have tried to make platforms to explain how to secure them. And we might as well start with the obvious one for Americans, the U.S. government. The U.S. government has made a risk management framework for AI. So this is probably the logical first place to go. It turns out this is not extremely practical. It's focused on a very high governmental level, thinking about things like federal government policy, as we're going to see. So it first specifies your harms to people's civil liberties or harms democratic participation or discriminating. That's the harm to people that an AI might do. Here's harm to an organization. It might mess up your operations, have security breaches, or harm your reputation. And to an ecosystem, it might affect the interconnected elements in the global financial system and the planet. So this is really at a high level, not at all the kind of stuff I'm usually looking for, which is what one company would want to consider when deploying AI in their company. This is all thinking at the national policy level. But they do have, so they have this typical really vague plan here of life cycle and key dimensions, where you have data and input, then you have your AI model that you have to verify and validate, and then your task and the output that comes, you deploy and use it, and then you have the context where you plan and design and so on. These are the various steps. You'll see these in a lot of these really big U.S. government frameworks that really apply mainly to the government itself and not so much to normal-sized companies below it. So you've got the application context. This thing, test, evaluation, verification, and validation is the process you have to do to see if this part is working. So first you design what you want to accomplish, figure out what you're trying to accomplish, and consider legal and regulatory requirements and ethical considerations. Then you collect and process some data. You're going to have to somehow get data. You're somehow going to have to clean it up and so on. Then you've got to build your model and verify and validate your model to make sure it's working. And then you have deploy and use your model, and now you're going to have compliance testing and validation to see if it is obeying your security policies and so on, and you evaluate how the users like it. And then you're going to have an application context where you run it and see what impacts it has, and this is going to come up again when we get to Copilot. There are problems with things you build that are not included, not intrinsic to the object. For example, you could build a toaster, and you could test your toaster for safety, like the electrical circuit doesn't short out, and it doesn't get too hot, and it pops up and doesn't set fire to things and things like that. And then somebody could put it on a high shelf so it falls off and hits people. And they'll say, there's a safety problem caused by the toaster, but it's really not got anything to do with the design of the toaster. And that's what we're going to see with Copilot. There are problems with the way it's used that really are not particularly related to the internal structure of the AI. Anyway, then you consider what effect it has on people. So one thing I thought was quite useful in the official National Institute of Standards document was this diagram. And when I teach the AI class, we go through all these types of models. But this is the interpretability of a model based on predictive power. The most powerful model, or the least powerful, and the most interpretable is linear regression, where you just put a line through some points. It's real easy to understand how it works, and a decision tree is very similar. A decision tree is just that series of if-then statements. If this parameter is above a certain level, go here. If this parameter is above a certain level, go there. And at the end, you decide whether you've categorized something in A or B. These are both very simple. Then there's something called K-nearest neighbors and random forests are more complicated. Support vector machines are even more complicated. And the most complicated of all are deep neural networks, like what's used by large learning models. And deep neural networks use layers of neurons the way your human brain does. And the problem is they are very powerful, but you cannot understand how they work. If you ask, why did you classify this picture in that category instead of that category, you can't find one neuron or one weight that caused that. The whole system works together to do something, and you lose the ability to understand why it's working. And therefore, you can't really fix it if it's broken, not easily. You can't figure out what part of it you would adjust to make it act differently. So that is a real issue. How inscrutable is your model? And here's what trustworthy AI should have. It should be safe, not harming humans physically, secure and resilient, just like other IT systems, explainable and interpretable, like I was just talking about, which is a problem with AI more than other systems. You often have something that works to some extent, but you don't really understand why it works. You consider the privacy consequences and whether it's got undesirable biases, which they tend to have. And then accountable and transparent would be a matter of taking sufficient logs and measurements to see what your AI is doing and whether it's doing bad things, and publishing those so people can examine and see what you're doing, and then valid and reliable is the end result if you can get it working. So that's a useful chart, I think. And here's the core of this thing. You have governing in the middle, and so you measure your tasks to see if it's working, you manage your risks, and you have a context considered. So this kind of big picture government thing that you get from the U.S. federal government. Now, the National Cybersecurity Center in the UK has published their principles, and these seem to be more down to earth, more down to the level where you can immediately apply them. They have these sections: prerequisites and wider considerations, then development, then deployment, continual learning, and then end of life. And they have details for each of these sections. So here you have the first idea, you're starting, you have inception, you decide your objectives, risk assessment, policies and compliance. What are you trying to build? What do you want it to do? Then you have requirements and deployment. So you have your technical gathering of training data and model creation, risk treatment. And then you have verification and validation, where you test to see how well it works and how bad the risks are as you develop your system. Once you've got it working well enough, then you deploy it. So now you're going to have to run it, have updates and risk management here, in operations and monitoring, and then in deployment. You're going to deploy it so people can use it, and then have, again, risk treatment of whatever flaws it may have. And then as you continue to use it, you're going to have continual online learning. As you use it, you're going to have to keep training it to handle new tasks and adapt to changes. So you'll be validating your data and risk management and continuous improvement here during the lifetime of using the product. And when you're done, you have the same problem you have in all IT systems, that you're, when you reach the end of life, you have to somehow clean up the leftover data. So you have to evaluate performance, refine objectives, do risk monitoring, lessons learned, and then when you retire it, you have to dispose of all that data so that no secrets are exposed. This is an important step in all these things like ISO 27000 compliance. You have to have a cycle where at the end you consider how well did this accomplish the goal, what were the flaws, and you try to make a better version next time. So you can keep improving, which is the only way to stay on top of things in the modern world. So that's the British system. Now, for even more hands-on technical look, we can go to OWASP. OWASP is the group that lays up technical flaws in technical things, like web pages and mobile devices, mobile apps. And they have two AI models, one for large learning models and one for machine learning models. This is the machine learning risks. This is thinking about something like those things that fit a line through points or that find the defective products on an assembly line. So you have input manipulation and data poisoning and several others. These are the top 10, and they're sort of a beta version form changing. The name of the first one changed just a few months ago. They're still developing it. So input manipulation is the most obvious one. This is why people wear like shirts with shiny patches on them. This is where you change the input data so the model will fail. So if you don't want a facial recognition system recognizing you, you could do something like put shiny makeup on your face and that'll confuse the model. That's input manipulation. Data poisoning is where if you can change the training data, then you can cause the model to behave in an undesirable way if you have access to training data. And this is something that is more practical than you might think it is, because most large language models, for example, are just trained on vast amounts of internet data. So you could just put a bunch of internet data out there and they'll probably suck it up and use it. Model inversion is where they reverse engineer the model to extract information from it, so they might be able to trick it into handing out more information than it should by carefully feeding it inputs. Then there's membership inference, which is very similar. You train a model on a data set of financial records, and then they can query it to find out if you're included. Again, you train a model on data, and then by building a similar model and analyzing it, they can figure out how to deduce things that you didn't intend to make public. These last two, 3 and 4, are very similar and a little hard to grasp. Model theft is much simpler. You steal the machine learning model from a competitor. It costs $40 million to train an LLM, so if somebody manages to steal your data, then they can have it without having to bother to train their own, and that did happen. I think it was Facebook that made an LLM, and they tried to keep it private, and somebody leaked it on the torrents, and so it became publicly accessible when they didn't intend it to be. And then supply chains, just like any other software, you have libraries that are being used, and you could poison the libraries, and they could end up in the final system. That's a big one these days. It's happening a lot to all kinds of systems. Then there's transfer learning. This is a quite common situation with large language models. You train them first on the whole internet, so they just learn the general parameters of English, and then you fine-tune them on your particular data. So first they've been trained on a vast amount of data, then you train them a little bit more on focused data for your company, and then ask questions about your company data. That's called transfer learning. So you fine-tune it on another task. And so that could go wrong. You could, if you were able to affect the data used for the transfer training, the little bit of training at the end, then you could make that model behave in an undesirable way. And then there's model skewing. You can manipulate the input data to deliberately make it come out wrong. And this has happened several times with political parties. When Donald Trump won the first time in 2016, the polls were extremely wrong. And many people worried a lot, how would the polls be so wrong? All the polls said Hillary would win, and then she didn't win. So, and one thing is, the Trump supporters had been told not to tell the truth to pollsters. And you could do that. You could, if you can somehow manipulate the training data, then you can make the model behave in an undesirable way and skew it to have some kind of bias. And then, of course, it's just another system, and it puts out some output, and then you're going to take that output and do something with it, like put it on a web page or put it in a PDF. And if you don't clean up the output might contain attacks, like cross-site scripting. So the output of your model might attack the user if you don't clean up the output. And then neural reprogramming. If you can somehow change the parameters of the model, then you can make the neural net behave in an undesirable way. One thing about this, like I was saying, is particularly for neural nets, this is very hard to do, because even if you gain the power to change some of the neurons, you don't know what it's going to do. It's not easy to calculate what change you would make to achieve a particular outcome. So that's pretty good, although quite a few of those, you can see why it's in a beta form. Quite a few of those are sort of vague and overlapping and confusing. The LLMs are in a more final form. OWASP Top 10 for large language models. Prompt injection is a well-known technique where you have a machine learning model like ChatGPT, and it has a bunch of security rules, like it's not supposed to tell you how to write malware or make a poison or kill somebody or commit a crime. And yet you can trick it into doing those things by wording your question differently. One thing that seems to work very well is to tell it that you're writing a play, and your character is a criminal, and won't you help it write about what the criminal is going to do, that sort of thing. So that's prompt injection. Then, again, insecure output handling. If the output is not cleaned, the output might contain cross-site scripting attacks or other things like that. If the training data is tampered with, then it will learn bad behavior, and this happens, in a way, it's happened to all of them. A lot of the current large language models will in fact tell you falsehoods, like the 2020 election was rigged and the COVID vaccine was poisoned and didn't work, because they trained it on just a whole bunch of the internet, and the internet has a bunch of bad information on it. So they will repeat that bad information back to you because they don't know what they're doing. Then, of course, remodel denial of service. Any public service that takes data from the public is subject to being flooded with unwanted requests. That's an issue. And again, supply chain vulnerabilities, as before. The models use libraries, and the libraries use code that comes from God knows where, and sometimes you'll get a bad version of a library. Then, of course, sensitive information disclosure. This is quite a problem. When you trained the model on all that data from the internet, it was not supposed to memorize any of that data. It was supposed to learn the trend, like the general structure of the English language from that data, not memorize whole pages of the data. But authors who wanted to know if their book had been included found that by putting in like a page of the book, it will repeat back 50 pages exactly of my book. So the current large learning models have apparently been overtrained, and they have memorized whole bunches of data, and therefore they can repeal sensitive information. If you did not clean all the training data to make sure there was nothing confidential in it, then anything you didn't redact might come back in the large language model. And this is a problem at companies that want to train on, say, emails or customer complaints or things like that that include some private data, that if you don't redact it all from the training data, then it will be in the model and it might come out again later. If you have plugins to handle special things like input of different languages or something, then they might have insecure input, insufficient access control. There's the possible weak spot. This is a big one. This is what's wrong, in my opinion, with Tesla cars. Excessive agency. You take a large learning model and you let it do something dangerous, like drive a car or drive a drone or shoot a weapon to kill people, and it's not really smart enough to trust it with that dangerous task. That's called excessive agency, where you let it do something that it's really not smart enough to be doing. And then over-reliance, this is where people trust it. This happened all the time. There are all these famous cases. There was a lawyer that used ChatGPT to write a brief and went to court only to be humiliated when it turned out that there were false statements and false references in the document, and this is happening all the time. There's scientific publications full of papers written by AIs that are full of mistakes and false statements and so on. This, I think, is one of the biggest ones that affects people in practice. People use it and they expect the answer to be reliable, and it is shockingly unreliable. I've seen some studies where up to 30% of the output is wrong. So that's pretty bad. And then, of course, model theft. If someone is able to somehow copy your model, then they can make a competing product and save a bunch of money. And, just like any other software theft, it's bad for your business. All right, and then we should talk about Copilot in particular. And the best article I found about Copilot was from a company called Varonis, which does make a product to add security to Copilot. So it's possible that they're just exaggerating these risks to try to sell the product, but it made some sense to me. Now I see some comments in the chat. Okay, are you suggesting that Tesla uses LLMs for driving? No, they're using machine learning for driving. You're right. Good point. Just the principle of over-reliance. That's all I mean. A very good point. No, I don't. They're not using LLMs, but they are using AIs of some kind. Good. All right, so Microsoft Copilot, what it does is it's sort of like ChatGPT for your company data in your Microsoft 365 account. Office 365 lets you have Word and Excel and PowerPoint and other things online, connected to OneDrive, connected to Microsoft SharePoint portal. So all this company data in many documents is all shared with you in the cloud, which is very useful for business, and almost everybody's using it. But Copilot now can do these things for you. It can join your Microsoft Teams meetings and summarize them and capture action items. So it's just going to turn all the spoken word into text and record it, like take notes. It can go into Outlook. It can organize your email, summarize threads. It can generate replies for you. It can answer email for you by reading it. In Excel, it can analyze your raw data and find trends and suggestions. So these are very valuable things. But what it means is it has access to all your documents. And the only limitation on any of this is your Microsoft 365 permissions. And this is the problem. The permission structure in Microsoft 365 is very clumsy and doesn't work very well. Let me check comments in the chat again. Using deep learning for sure. Yes, that's right. Good. Yep. All right. So this is Microsoft's diagram of how Copilot works. So you have your Microsoft 365 apps up here like Teams and PowerPoint and Word, and your user types in a prompt in one of these. They adds a Copilot option. So you say, okay, I want to summarize this whole email thread and write like a PowerPoint presentation about it or something. So then it goes down to pre-processing to Microsoft Graph, which has learned your context and content, and it has done this by reading all your files and chats and emails and everything. This is the dangerous spot. The Microsoft Graph they've taken a large language model that was trained on a big corpus of data, and they have added the second training, the fine-tuning on your personal data, which they find all through the Microsoft Office ecosystem, Microsoft 365 ecosystem, and that's what does it. So they don't send your data then they create a modified prompt, including all this data, to the large language model and get the response. So this is how it works. And of course, on the good side, it will do a very good job. You can say, summarize this email thread where I'm discussing something with a vendor and make a project proposal out of it. And it will say, oh, there's a shared file somewhere, and the shared file is relevant to this. And there's an Excel spreadsheet relevant to this, and I'll include all that information to improve it. When it works, it's of course very valuable. All right, so what Microsoft handles for you is tenant isolation. One person is logged into Microsoft 365, and only that one person can get the answer, and it will only use files that one person can see. If you are not authorized to see a file, then it will not be included, of course. And that's also training boundaries. It doesn't train on any of your user data. This is an important issue. It has trained this model on some other data, probably the heap of data just off the internet. It includes your data in the query. It adds it to the prompt. That's why modern models make a big deal of, we can take 100,000 words, we can take 200,000 words, because even though you write maybe 5 sentences of what you want, it's going to add thousands of pages of stuff it finds here to the prompt that goes to the large language model. And that's how it includes your specific company information. So you get an answer that is informed by all the relevant information from your company. You don't get a generic answer just based on random data it found on the internet. But what you're really getting is a mixture of random data from the internet and the specific data from your company. In the best case, when it works right, it takes the English structure that it learned from the internet and combines it with the facts it finds in your company data to give you a properly formatted English response that is based accurately reflecting the information in your company data. That's the idea. And so it does not train the model on your data. It just includes it in the query so it can answer a question informed by that data. And so here's what you need to manage. You need to handle the permissions. You need to limit what files each user is allowed to see. You need to put security labels on your files: confidential, secret, public, and you need to locate them everywhere. They will not inherit the labels. This is a huge problem. This is probably the biggest problem here, the whole point. If you have some data and some emails that are sensitive, that are not public, it doesn't have any way to know not to include that information in the output. And you might just share the output publicly. So it's up to the human to notice if any of that information came from a document that is not really public. And that is a very difficult job for the user to do. And this is, of course, there's the problem with humans, over-reliance again. The answer might not be factual or safe. It might say things bad, it might say things wrong, it might say things that are harmful, and humans would be responsible for this. So this kind of undoes all the benefit. I mean, it does the work for you, it produces something that looks good, but you really have to review it carefully because it might make these kind of mistakes, and that's a problem. And here's some interesting statistics from Microsoft. Multi-cloud environments are complex. There are 40,000 permissions or more to manage. Over 50% of them are high-risk permissions that would expose too much data. They found that most identities are greatly over-permissioned. Most people have too much permission. This, by the way, is very common when something is new. When you make a When you share a file in some environment, if you have trouble with permissions, you just share it with everybody. You need full access to everybody. When a program doesn't run, you just run it as an administrator to give it full access to everybody. The easiest way to make something work when you're having problems is to just remove all the security barriers and run everything, opening all permissions. And this is apparently what a lot of people are doing with their machine learning systems because, of course, they're complicated, they're hard to set up, and so they just give everybody lots of permissions to make it go. Let me check the chat. Yeah, all right, good. All right, so workload identities accessing cloud environments are increasing, outnumbering human identities 10 to 1. So 90% of the identities are not humans. They are agents and bots and services coming up there. So it's even less likely that anybody really carefully configured them to have the right permissions or is checking those permissions. 1% of permissions granted are actually used. This is another really large clue that you are giving people way too many permissions because the permission model is too complicated and people can't figure out how to use it. And here's another one. 50% of identities are super admins, have full control over everything. This is a really bad idea. This is what happened to Windows up through Windows XP. Everybody ran everything as administrator, and so you get your machine infected all the time. So anyway, that shows that the current permission model is not in fact working very well at all. And I must say, all the cloud security training talks a lot about this, how to somehow manage identities and form groups and control the permissions over your cloud environments. This is an area that is very difficult, very confusing, and very often done wrong. The average Microsoft 365 tenant has 40 million permissions, 113,000 sensitive records shared publicly, and so on. This is what they say. This sounds unbelievable to me, but that's what their study showed. And it happens because there's direct permissions assigned to the user, then there's group permissions, SharePoint permissions, guest access, public access, link access. There's just a lot of ways to share something. And those permissions are many holes through which a mistake can be made. And Microsoft has their answer for this, which is something called Microsoft Purview Data Security. But you have to enable sensitivity labels for SharePoint and OneDrive, and humans have to faithfully apply these labels all the time. Microsoft does have some system attempting to mark sensitivity labels on documents, but I don't think that the AI machine can really properly propagate those permissions. It supposedly will label the output with the sensitivity label of the most sensitive input it used, but I'm very skeptical that it's actually working from these other measures. But that is certainly the issue. Anyway, that's what I wanted to show you, and I'll just point out there are some projects you can do for extra credit here. This is on my 128 page. If you go to the projects, I added another block towards the end. These are not hands-on projects. These are just sort of like quizzes. They're like the, so if you go here, each one of them is worth 15 points. You go here and it asks you a question. An attacker backdoors the library. Which risk is that exploiting? And so that is supply chain. It's a supply chain attack. So if you say that, you're right. Now you have one correct. If you get 5 in a row correct, you'll get the flag. And you can then turn it in or put it in the automated scoreboard. They're all like that. They're just ways to encourage you to read and learn this stuff. And each one of them has a link at the bottom to the source document you can review. So the people in my incident response class will see this is also how I handle learning the attack framework. So anyway, there's things you can do for extra credit if you want to, just so you begin to see some of these security issues and the recommended security procedures. And that's all I wanted to show you. I'm going to stop this recording.